Hello,
Professor.
hello. That was
Good
Osmail.
afternoon, Professor.
Oh, good afternoon. That was wait. Oh, who I missed who that? I know it was Osmail, and then it was and hello, Jamalet. I mean, good afternoon, Jamalet. All right, not that it matters. Well, it does matter. Who was that right after Osmail? I'm just trying to get my. But who? No one's gonna tell. Oh, is Jay Lynn? No. Okay. It what? Whatever. Okay. Hello, hello. Good afternoon. All right, I'll do that. So I'm saying hello, Jay Lynn. Hello, Abdel. Hello, Sarah. Hello, Brianna. Hello, Ashley. Hello, Samuel. Hello, Osmail. I said, hello, David Kahn. Hello, admin. And now I know who admin is. Wait a minute. Don't, I believe, if I'm getting this right, I want to say that admin is the book of Samuel number, is the other book of Samuel. Is Sam a J-ho? A-J-A-O. Tell me if I said that right. Yes. And I'm saying, and am I saying your last name right after 14,000 semesters? Am I Yes. All right. Well, so we'll see. Someone has learned something. Okay. I want to graduate to 205 now. Thank you. All right. No, cool. Okay. Okay. And also chat wise, good afternoon, Jamila. You know, this part of this class, I don't know if you're sick of, my family is sick of over here. They're like, we hear you every single day. We don't learn any physics, but we know the names of your students. It's really great. Okay. Good afternoon, Jamilet. Good afternoon, Jada. Good afternoon, Diana. Good afternoon, Sophia. Good. Hello, Gianna. Top of the afternoon, Abdel. Oh, okay. And thank you, direct chat person. I won't say ice cube, but no one else knows what I mean when I say that. Okay. Thank you. Okay. Sorry. Thank you. Got it. Direct chat person. And good afternoon, Samuel, book of one. Good afternoon, Stephen from 2D. I feel like at some point, Stephen's just automatically going to graduate to 5D just from the number of 2Ds that he exists in every day. Okay. Hi, Jasmine. Good afternoon, Amy and Ice Cube. Amy Kanina. Good afternoon, Sarah. Good afternoon, Chloe. Good afternoon, Jaylyn. Hello, Samuel. Ajayo. Good afternoon, Brianna. Okay, we're up to. Okay. Thank you, direct chat person who was helping out your other direct chat. Oh, and direct chat person who's helping out a colleague by saying that they're having issues. Electronic, feel free to submit that for multiplayer co-op. I mean, if that's not collaboration, what is? Good afternoon, Nicholas. Good afternoon. And GoPod afternoon, David. Okay, see, it sounds like I'm correcting his spelling. I'm not. I know that was just a typo. Okay, good afternoon, everybody. But I also did not say, wait, I said Diana, Sophia, Gianna, Jamilet. Boy, for a guy who says he doesn't take attendance, he really does seem like he's taking attendance, doesn't he? And for a guy who says he doesn't talk about himself in the third person, he really seems like he talks about himself in the third person. Okay, Gianna, Jamilet, Stephen, Chloe, Jada, Jasmine. All right, hello, everybody. Yes, let's do physics. Right, 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 right. Oh, and hello, the one person who's really, and there's Brianna, she's back. Not that I'm eavesdropping visually. Okay, but I am. Oh, and three. Oh, yes. Okay. Wait, good question in the direct chat. We're gonna get rolling. There is an actual sub. Oh, and hello, Nicholas. Sorry, I'm not trying to point out you go, but hello, it's great to see you. Wait, there's a great question in the direct chat. Now I actually have a dilemma of whether I should just answer it in direct chat or in. Okay, wait, I'm gonna answer it in direct chat. Hang on one second. Hold on. Well, actually, I am going to answer it to everybody. Hold on. There is a good question in direct chat. I'm going to put something in the chat here just in case. This probably belongs in Google Classroom also. I'll try to remember. Hold on. And other people are here, I know. Hold on, sorry. Um, 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 okay. Oh, well, sorry. Okay, sorry. In the chat is stuff. Actually, I think this is in the syllabus in the Google Classroom, but this is important information that, you know, it's like exactly that kind of information that no one, you don't need it until you need it, and then when you need it, you need it. So if you ever want to visit me physically in person in 3D, the time in general to anybody and everybody is 11 a.m. to 1 p.m. Tuesdays on the 4th floor of the new building. In my office, my research lab is on the 4th floor. It's near the elevators. I mean, it's not in the back halls, blah, blah, blah. It's near the jaywalk, actually, windows to the jaywalk on the 4th floor, on the south side, the men's bathroom side. And anytime between 11 and 1 in general it's not only the best time, and you don't need an appointment. You don't need an appointment. It's not only the best time, but realistically, honestly, to spontaneously visit me physically, it's like the only time, because I'm not in New York that much these days. I'm not in the building that much these days. That's the time. I'm happy to make phone calls, Zoom appointments with anybody at any time. And we make the appointment by text me, and we'll figure out if you want to have a phone call or a Zoom call or whatever at any other time. So that's for everybody. But also, I'm glad someone just reminded me of this question, because tomorrow I might be there very, very briefly if you have a quick thing, or you're right at the top of the hour at 11. I might be there very briefly at the top of the hour, especially if you have something urgent or something you need signed or something. But I am leaving early tomorrow, because to tell you the whole truth, because my brother, who's in FDNY, is being promoted to lieutenant tomorrow. We're all very proud. I'm very proud to be his brother. I'm very pleased. This is a slight surprise, blah, blah, blah. So that's tomorrow. So I totally want to go be part of that. That's my reason or excuse or whatever. And I apologize, but generally that's where, okay. Generally on Tuesdays, 11 to 1. Okay. But thank you for asking. Okay. And and I have to get the board back up. We're going to do some physics today. We're continuing to roll again. Also, sorry, logistically with the main homework, the spring homework, it was technically due last week. If you made any attempt, you got for last week, you got a lot of starter points just for making the attempt. That is not your final score at all. Just to remind you, you'll get more points as you do more on it and make more corrections or finish it more, or I look at it in more detail as we continue to go over it. I'm talking about homework 1B right now, but even technically, but nobody's late or anything like that. Technically it's still due tomorrow, this Wednesday. So even if you've never made an attempt on it yet, you can still get ultimately all the points, blah, 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 blah. So the homework that's on the docket right now for both you and me is homework 1B. We're going to continue talking about that today. We're going to do more concepts that underlie it. I'm going to back up on it. So, because I know I've already given you a bunch of answers. I know that, and sort of solutions that you could use to hand in through questions 5 or something like that. But I want to start now back up and really talking about concepts that we have to extract from that and use for the rest of the semester. Okay. So bear with me, but things are still happening in the direct chat. Bear with me for a second, but that's what we're going to do is continue to go over the concepts of homework 1B. Sorry. Okay. Okay. So I'm going to get the board working. Okay. Yes. Okay. Bear with me for a second. I'm going to get this board up. Yeah. Okay. And obviously, so I'm getting the board up and we're going to get going here on physics. But of course, again, there have been a couple of questions in the direct chat that I've either answered publicly or directly, depending, but keep them coming. I mean, I think last time you guys were great and your participation was actually phenomenal. Okay, that should be my board entering. Yes, okay. 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 What we're going to do. Okay, as you can see on the board, what I'm going to do now, and again, stop me if I'm like wrong, but I believe we've given a solution to question 4, and we've given a solution to question 5, and we got answers for both of them. And pretty much what I wrote down would be pretty much sufficient for you to write down if you were handing it in for homework, assuming you pretty much understood what I wrote down in terms of the GDP, the general definitions and principles, and the work and all of that. But what I wrote down for question 4 and 5 had to do with kinetic energy and potential energy. And that my ultimate statement in question 4 and question 5 was that if my big statement, my GDP, okay, I'll remind you right now. Okay, this isn't the exact words, but basically the big point that we made as our GDP, as our general definition and principle, as our step 3 of the problem solving method, the big statement that we made in solving question 3 and question 4 on homework 1B was we said, okay, when all the forces doing work on a system are conservative forces, when all the forces are conservative forces, then we said total mechanical energy of the system will be conserved, will be a constant number, will be an unchanging number from any one location, position, point in space to any other point in space. That is our big claim. Now, there's no tricks up my sleeve. That claim is definitely true. Like, that's a huge principle. That is, in effect, the statement of what we mean in physics as energy conservation. That the total mechanical energy of a system will be the same over here as it is over there, if and only if all the forces doing work on the system are the kind of forces that we call conservative forces. Okay, now that's totally true. You can take that to the bank, you can memorize it, whatever. But there's a lot going on in that statement. I'm using it, but there are a lot of words in there and a lot of like description stuff that I think need to be broken down to understand, like to know when to apply the statement and what it actually means. For the simplest thing to say that I've already said is, please note, for what it's worth, it took me years to realize this. Like, energy conservation means the total amount of energy is one number that never changes. I mean, I think that you all understand, you've seen that before. And that's what we're always looking for in physics, is a number that doesn't change while a bunch of other numbers do, right? But I do want to once again make clear that there's other kinds of conservation theorems in physics and chemistry and so forth. There's a such thing as linear momentum conservation. There's a such thing as angular momentum conservation. Oh, there are other kinds of things that get conserved. And a big difference is when we say that energy is being conserved in the system, we mean from spot to spot, as opposed like from position in space to position in space. So in the case of this mass on the spring, if we're claiming that energy is conserved, what we mean is whatever the total energy is while the spring is right here at x naught, that total amount of energy is going to be the same when the spring is over here at x equals 0, right? And so ultimately we use this theorem when, to be more specific, if we know the speed over here at one spot, and we wish to know the instantaneous speed of the system, and I do mean specifically speed, like that's not an arbitrary example. That's like always what it comes down to. If we know the speed over here at one spot, and we wish to know the speed at another spot, that's a kind of problem that should invite or trigger mechanical energy conservation, as opposed to if you ever have a system, and it doesn't come up with as much in physics 204, but it might come up in other classes or other studies. If you ever know the speed at one time and you wish to know the speed at another time, like say you know the speed of a bunch of cars right before a collision, and then you want to know the speed of those cars the moment after the collision, when they exit the collision, that's a very similar type of problem in a way, but what you would use there is linear momentum conservation. Energy gets conserved from place to place. Linear momentum gets conserved from time to time. Just that's one, and especially any of you, those of you who are going to take like the MCATs or any other, if you have a standardized test or some kind of study where there's a lot of different physics topics that come up, where it has a physics section, like even if you're not going to be a physicist, if it has a physics section and a lot of different types of questions, the MCAT is definitely one such example, or the GREs. Like one of the difficulties in life becomes knowing which physics to use for what type of problem. So I'm just telling you right now, if you know where you're going on in life, like make a note somewhere in your notes. When you're trying to transfer knowledge from point in space to point in space, we use energy. When you're going from point in time to point in time, like before a collision to after a collision, or before an explosion to after an explosion, then you use linear momentum conservation. Now, again, that one doesn't come up as much in this class. So I'm just sidebarring that and saying, okay, so that's statement number one. But now, the thing I really have to expand today is there's this whole condition, this statement, when all the forces doing work on a system are conservative forces, then we use total mechanical energy conservation. Well, this idea of the mass on the spring that's going back and forth, it does pass this test. We inspected it, and I said to you, oh yeah, this is one of those times. The force, and I said, the force doing work on the mass is the spring force. There's no other forces doing work on the mass. The only force doing work on the mass in our problem here is the elastic Hooke's law spring force. And I said, and that force is conservative. So, okay, we passed the test and we applied energy. But where did I get that from? What I want to talk about today in a little bit of depth is, what do I mean by a force doing work? And what do I mean by saying a force is conservative or not? Like what, because that we need for the rest of this course. So again, let me just remind you, if this is a little bit nonlinear to people, you already have your answers to question 4 and 5. I'm now going back to question 4 and 5 and going underneath and explaining more where those answers came from. Everything I'm saying now ought to be, you don't have to write this all in your actual homework set solution if you've already done it. I'm not saying you have to add this to your homework. I'm saying that this will hopefully, this is the purpose of the homework, and this will, if you haven't done it yet or whatever, hopefully understanding this would make you in a much better position to do your homework in an honest, clear, confident way. But okay, but this is I'm unpacking what we've already said about question 4 and 5. Okay, I'm going to back. So I want to explain what I mean by work. And I know I explained it to some extent to some of you, and Hema or Professor Walters explained it to some extent to some others of you, and others of you have gotten it maybe in great depth in high school. But to bear with me, I think I'm going to explain it in more depth today than maybe you've seen it anywhere. And I'm definitely going to explain it the way that we need it for this course. Again, the it that I'm going to explain is work. So any knowledge you have from before, good. If it makes you more comfortable, you can hold that knowledge in your mind, but you don't need it. You can wipe it out too. This is blank. We can act like we are not at all comfortable with what work means, whatever. So I'm going to start by saying that weird thing that looks like a 3 with it, that's supposed to be a lowercase z the way I did. So it doesn't look like that's the way I draw z's. I don't know why, but so z stands for some general measurable variable. Okay. I'm going to use lowercase z just to mean a variable in general. I'm going to introduce some notation here to be clear. Then from here on in, as you've seen in math before, delta z, right? From now on, like you say in math, sometimes delta z means change in z or something. But what I like is the word that I like slightly better than change is difference. Delta z means difference. Specifically, from here on in, if I write delta z, again, z meaning any variable at all, could be x, could be y, could be q. But if I say delta z, I mean a small but finite difference in two values of z. So specifically, I mean, when I say delta z, I mean like z2 minus z1. Just like in math, when you say slope is delta y over delta x. So what do you mean by delta y? You mean like a small but finite, and don't get hung up on the word small, but the key point is that you mean finite. When you say delta y over delta x is slope, delta y stands for y2 minus y1. It's the difference as in like literal subtraction, the difference between two nearby values of y, y2 minus y1, right? Or x2 minus x1. So in general, just to remind you, when we say delta z for any z, we mean the difference in two values of z. Okay, however, that's to contrast with okay, and say okay. All right. So now you've seen this too, but let's just like get it explicit. If we switch from, delta, the lowercase Greek letter delta is like the equivalent of d, so it's like delta for difference, right? But if we switch to an actual lowercase d from the Arabic from our alphabet, from our English alphabet, if we switch to an actual d, then what we're saying, let's be explicit about this. When we say dz, we mean a difference in two values of z when the two values are infinitely close to each other, or perhaps, right, we mean an infinitely small difference in two values of z. Or if you like, an arbitrarily, we mean the difference between two values of z when the two values are arbitrarily close to each other. When the difference between the two of them goes to the limit of 0, right? Now, this is where we start getting into calculus, right? A limit means as close as you like without, the limit as you approach 0 means as close as you possibly want or possibly have to 0 without actually getting there. Now, that sounds at first like a very nebulous, very abstract, it sounds, at least it did to me, like a very disorganized, very unclear, very imprecise concept. It sounded like the kind of concept that maybe I could imagine in like a philosophy class, but I wasn't like looking for in a math class, I thought. It's actually a very precise concept. It's a very weird concept and a very hard concept in a way, but it is a precise concept. When we go to the limit, we're saying when we go to the limit as a quantity approaches 0, how deep do I want to get into this? As scientists, it means something very specific. It means the fastest, most concrete thing I can say about limits or about infinitely small, or really about infinity. Infinity is very, very real in math and science. It's heady. It's possibly challenging as a concept. Maybe it's very exciting as a concept, but it's very real. The infinitely large and the infinitely small really mean something, and they particularly mean something. And this surprised me, and it really delights me every time I think about it. The place where I would think infinitely small would mean the least would be not, I would think it would mean nothing in math because it doesn't sound precise and exact the way I thought math was supposed to be at some point in my life. It sounds even like it has less of a place in science, if science is supposed to be about the real world, and particularly the measurable, observable reproducible, quantifiable, concrete world, if that's what science is supposed to be about, I certainly thought that talking about something that's infinitely small in science made no sense when I first heard about it. But in fact, the science class, or the science lab, is precisely the place where talking about infinitely small makes the most sense, or makes a lot of sense, for at least this reason. When we say from now on dz, or any variable, dx, dy, right? When we say d, we mean infinitely small interval. And by infinitely small, what we really mean in a scientific context, in the context of that which we believe because we measured it, to say something's infinitely small means it's big enough to affect measurements, to be making a difference in measuring devices and in an experiment, like an electron, electron's a good example. Like the size of an electron, can be picked up on measuring equipment and on oscilloscopes and stuff like that, or electron microscopes, and clearly the size of an electron is affecting other electrons and affecting things that they do that we can measure, like velocity or energy and stuff like that, maybe energy more likely. So the size, the radius, the volume of an electron is big enough to make a measurable difference in our larger measurements. But so it's not zero, is what I'm saying. It's not zero, it's something. But it's so small, and now I'm talking like the radius of an electron, and therefore the volume of an electron, is so small that it's too small for any measuring device to actually put a number to. It's between the cracks of any measuring device we have. So this is equivalent to like lengths that are, if you have a meter stick that's then divided up into centimeters, right? A mosquito is big enough to see if you put it next to a meter stick. A mosquito doesn't have zero size, but it's not even as big as the space between two of the closest markings on our meter stick. So we can't give it a size with that meter stick. We'd have to go to a smaller meter stick, but for 1,000 reasons, maybe we can't. So a mosquito, you can't say is a centimeter in size. It's not that big. But you can't say it's a half a centimeter or a quarter centimeter. That would be lying. That would be defying the whole purpose of our measuring equipment and measurement as a process. So what is a mosquito? It's between 0 and something in terms of its size. It is the length of a mosquito, at least if we used a meter stick to measure it, would be a DZ. Okay, I'm getting myself a little bit, but that's just my quick argument for why when we say infinitely small, if you want a fast word for what infinitely small really means in a science class, it means immeasurably small, but still existing. That seems like a concept that we need to have, as far as I'm concerned. If all we, all right, I'm going to stop selling it, but so far, now you might, of course, where am I going with this? I'm going somewhere. I'm going to calculus land. Obviously, today I'm trying to like fill in some calculus that you may or may not be comfortable with and link it to physics. Oh, that's either good or bad, depending on whether it's bad or good. So DZ, so delta Z means small but finite difference between two values of the variable Z. DZ means two values of the variable Z when they're infinitely close to each other. And I'm going to give you one more piece of notation that we're going to need later. We're not going to use today, but one more just to complete this package. From now on, we're going to say this D Okay, just as a last piece of notation, which we're definitely going to have to use for some more advanced calculus that we're going to do a little bit more down the line in this course. whenever you see that weird thing that looks like a backwards delta or so, I don't even, or backwards 6, I mean, that symbol, it doesn't have it's not actually a Greek letter, maybe a Celtic letter or Celtic letter or something like that, but whatever it is, we just read it in physics as partial. If you ever see that symbol, and you will in this class, if you see that thing next to a Z, you would read it out loud as partial Z. And what that is a partial differential. Like I should have said, delta Z, what we first wrote down, is a difference. Then DZ is a differential. In fact, I better write that. Hold on. So this thing here, delta Z, this is a difference. Delta Z is when it's finite. When it's infinitely small, we call this a differential. Notice I'm not saying derivative yet, because it's not. I'm saying a dz, a d something, is a differential, which just means infinitely small difference. And please note that, like it's the only leap between delta z and dz is just that we leapt from finitude to infinitude, right? And that is a leap, but that's it. Anything else you remember from calculus, all these other complexities, don't bring them into your mind yet. Like dz is a differential, or dx or dy. They're not derivatives. They're differentials. They're just infinitely small difference. They're just the concept of delta z taken to the limit. Okay, that's called a differential. Then I'm going to say, if you do this weird piece of notation, this is called a partial differential. And we use this piece of notation, we will use it a lot later. We use this piece of notation when we have some function, some other variable depends on z, and that would have been true for this whole discussion so far. But in any context where some function depends on more than just z, any function that's called a multivariable function, when z is not the only variable, and things change as a result of a bunch of stuff, and z is just one of those factors, then we build from this things called partial derivatives instead of full derivatives. And we have to get it. So this is part of multivariable calculus, which we have to get into in this class soon, for the first time for most of us. Okay, so just as notation, just to build up our calculus terminology, delta z means small but finite difference in two values of z. dz means infinitely small difference in two values of z, i.e. a differential, and partial z means an infinitely small difference between two values of z when z is not the only independent variable in some function, i.e. it is one of a bunch of partial rates of change that come together. Okay, now that's notation. That doesn't do anything for anybody I know in terms of this physics problem yet. But now I'm going to say, okay, given this above notation now, just looking at the time. Oh, okay. Oh, we're fine. And please stop me if there's any questions or blah, blah, blah. Given this above notation, I'm going to define some physics now. Wait, sorry. Hold on. That's not incorrect, but let me just say one other thing before I say it. Okay. So I'm saying right now, I'm not defining work yet. I'm defining a small but finite amount of work. I'm defining it as the scalar product of two vectors, one of which is small but finite. Okay, let me quick example. Okay. All right. So for example, now again, some of you have seen this example before, but I want to trust me, please, or bear with me. I want to extract and flesh out some details of this example that I think maybe some of you have not thought about before. So what, in simple terms, what I'm saying is that for a small amount of work, that is to say, over a small but finite displacement, work equals the scalar product of the force vector with the displacement vector. The Okay, first of all, in this example, where I'm saying work is the force vector times the displacement vector, I'm saying this is an example where a small amount of displacement multiplied by a force is going to give us a small amount of work. And I keep saying small like it matters. It does matter. So but then I put 5 meters in. So a very reasonable question one might ask is, if 5 meters is small, what the heck is big? Like, what does he mean by small? How do I know if 5 meters is small or not? Very good question, if you're thinking that at all, or anything like that. Here's the answer. What I mean by small is what I mean by small, very specifically. What I mean by small, well, just again, we're scientists, we're actually practical. So all these vaguenesses are actually less vague than they sound like. Just like before, when I said, what do I mean by finitely big? What I meant was big enough to be quantified on a piece of measuring equipment. That's really what I mean by like bigger than infinitely small means big enough to be measured. Well, similarly, if I say that the displacement here is small enough to use this equation, what I mean is that for the circumstance, it's small enough to prevent F from changing. I mean, the independent variable is small enough to hold the dependent variable constant. Now, what that actual number is will differ from circumstance to circumstance. But when I say small here, what I really mean by that condition is oh, it looks like we've been given a constant value of F. It looks like this F is holding steady at 20 newtons for the entire duration of the 5 meters. Maybe if I had let it go like 100 meters, by that time, the person, sorry, this is supposed to be a person pushing a box across a floor or something like that, I should have said. This is like a person pushing a box across the floor. So they're pushing at some angle, but the box is like sliding along the floor, let's say. So maybe if they pushed for far enough, they eventually would get weak and the force would change or something. But I'm saying, let's just assume that this is a quick enough situation that the force holds steady at 20. So the delta X is small enough to allow us just to pick one value of F and multiply. It's small enough to keep things simple like that. So first of all, what I mean by small is small enough to prevent F from changing, to hold F at a steady value of F naught, whatever that is. Okay, that's an important condition. Our equation that I'm giving you will work as long as that condition is met. But then two, okay, I gave this equation over here that said delta W, small amount of work, is equal to the force vector multiplied by the small but finite displacement vector. But I didn't put a vector symbol over on the left side of this equation. That was not a typo. Work, whatever you might or might not remember about it, work is not a vector. You can do positive work or you can do negative work. Just like you can have a temperature that's above zero or a temperature that's below zero. But temperature does not have a direction, and neither does work. It's just an amount. It's just an amount. It's a scalar. So how does that work? How does that happen? How is it that we're taking two vector quantities that have direction and multiply them so as to get a scalar? Important question. And the answer is, oh, wow. And okay, sorry. Okay, the answer is we're multiplying two vectors in a certain way. There is more than one way to multiply two vectors. We need this concept for this class. And I'm telling you, I'm teaching it to you. I'm not assuming you know this. Maybe some of you do, which is all great. If you do, that'll help you. But what I'm about to say, I'm not assuming anybody has seen before. And I'm teaching it to you right now. There's more than one way to multiply vectors. Actually, well, yeah, no, I'm not going to write it down. I'm going to get confused. Actually, there's three ways to multiply, three basic ways to multiply vectors. You can multiply a vector by a scalar. And when you do, you always get something that is a vector. Or that's choice number one. That's way number one. And it's just called multiplication of vector by scalar. Like there's no name for it. It's multiplication of a vector by a scalar. And you always get a vector. There's choice number 2, which is you can multiply two vectors in a manner that produces a scalar. That's what we're doing right here. That is called the scalar product or the dot product. I'm about to write that down. Or there's a third choice, which we also ultimately need to know for this class. You can multiply two vectors in a manner that produces a vector. And that procedure is called the vector multiplication of vectors, or more commonly, the cross product. Whenever you are faced with two vectors, you have two choices mathematically of how to multiply them. You can multiply them using something called a dot scalar product or a cross vector product. And you choose which one, and both are valid. Just like if you were ever walking in the forest and you face two numbers, you could add the two numbers together and get a certain answer, or you could multiply the two numbers and get a certain answer, or you could divide or subtract. Like there's different things you could do. And what you would do would depend on what kind of problem you're trying to solve. Like whether you're right. I mean, whether you're accumulating fruit or losing fruit, you would add or subtract. But numbers themselves don't call for any particular procedure. Similarly with vectors, if you're faced with two vectors, you can choose to multiply them according to the dot product. And if you do, you will get a scalar value, or you could do this other procedure called a cross product, where you would get a vector product. Now, right now, what I'm going to focus on is the one that we choose to use. So there's two mathematical choices as physicists in this physical context. When we are defining and then computing work, we choose. It makes sense for us. Because work is a scalar, we choose to do what is known as a scalar product, a dot product, and this is how it works. Okay. I'm going to say more about that. So I'm back in for a second. I'm saying, in general, what's the dot product? The dot product takes two vectors, multiplies them together, gets a number. What does the number represent? It represents a combination or a relation of the two sizes of the two vectors to the extent that the two vectors share a direction, to the extent that the two vectors are parallel. What the dot product does, hold on. Well, so that's what I wrote there. My handwriting says, so mathematically, the A vector dotted with B vector produces the length of A times the length of B times the cosine, specifically the cosine of the angle between them. This is in general, and then I'm going to apply it to forces and displacement.
Professor?
Oh, yes, I'm sorry, yes.
Could you go back 1 second?
Absolutely. I love that question. I'm totally, yeah, sorry. And by that's the most like legitimate question in the world, and only people that are even trying to do this class would ever ask that. So I got to open up a portal for anybody who ever asks me to go back. Yes, just let me know when I should. Yes, absolutely. Sorry.
All right, thank you.
Awesome. Thank you. That's great. Oh, wait, and that was that. Now that's the other. Wait, was that a coincidence that I just got the other Sam? Okay. Well, anyway, awesome. Awesome. Okay. So now let me explain this. Now again, and I warned everybody. I hope this is a. You notice I'm like it's almost like this is like a personal board meeting that I'm having with myself here. Like I know you all did question 3, and now I'm so deep into something so mathematically abstract. It may be very easy to like even know. I mean, it may be hard to remember like how what I'm doing has even to do with question number 3. And I know that. Like I'm hoping everybody's hanging with me. Obviously, the 2 Sams are. But I'm trying to back up on the math underlying certain physics concepts again, because I promise you we're going to need to expand on that math and those physics concepts later. And again, that's really what, just so everybody understands, that's the purpose of this homework 1 and why we spend a long time on it, because it's like a it's like a mini syllabus sort of, or a mini like I don't know what, like there's just a lot of the physics of the course is contained sort of in these questions of homework 1. So this is eventually going to relate back up to work, and work is going to eventually relate back up to conservative forces, and conservative forces will relate back up to energy. I'm doing, and I just again to warn you, like I hope you understand, I've given you the answers already, so we can hopefully be a little bit calm about that. But now, this all just could be just random lectures, but hopefully it's at least tethered to something slightly more concrete, which is just like the stuff you're trying to get together on homework 1. I don't know if that anyway. So what I'm talking about right now is any just 2 random vectors that you have, vector A and vector B. That if you want to multiply them together and produce a non-vector number, if you want to measure them in a way that ultimately gives you an answer that ultimately does not have direction, what you really want to do, what you're really going to do is this. Hold on. What I'm saying here is if you just have a random vector A, right? Just a random vector A, it has a length and has a direction. So its length is the length A, and its direction is, and its angle is theta. I mean, its direction as measured from the x-axis is theta. Remember from physics 1, if you just have this one vector, you can divide, one vector is the sum of its constituent vector parts, its constituent vector components. Right? Like the x component of A, the Hold on. Backing all the way up to vectors in general, just remember, if you just have this vector, think of it as like some arrow sticking out of the ground up at some angle theta, right? When we use SOHCAHTOA, when we divide A into a right, when we call A the hypotenuse of some right triangle, and we divide it into two perpendicular legs, one for each of the two perpendicular axes in the coordinate system in which A lives, right? When we say that the length of the X component of A is A times cosine of the angle, and that's like, because adjacent, I can back all the way up on this, but SOHCAHTOA, like the cosine of the angle equals the adjacent over the hypotenuse. Therefore, the length of the adjacent equals the hypotenuse times the cosine of the angle. So when we say that adjacent leg, AX, equals hypotenuse A times cosine of the angle, theta, what we're really saying is that horizontal arrow, the length of that horizontal arrow is like the projection of A onto the x-axis. It's literally the length of the shadow that would be cast by A. If A were an arrow sticking out of the ground and you had a light fixture above and you shined a light down on A and you just look at it and how much light was blocked on the ground below it, and you looked at the length of that shadow below it, that's how long it would be, A cosine theta, right? And if you shine a light from over there onto a wall, the length of that shadow on the wall would be A sine theta. So A cosine theta it's not the full length of A. Of course, it's necessarily shorter than the length of A, but it's the percentage of A, really. It's the fraction of A that got cast down onto the x-axis. And I hope it's clear, let me go one step further, that the smaller theta is, the bigger a percentage would land on the floor there. Like the smaller theta is, the bigger the horizontal leg would be, and the smaller the vertical leg would be, right? So now, like the smaller theta, because sine of 0 is 0, sine of 0 is 0, memorize it if you haven't. The sine of 0 is 0. It's like, and then as the angle gets bigger and bigger, sines get bigger and bigger, just like you would want if you made up that function yourself. Sine is super that way. But cosine is the other way around. Cosine is crazy or counterintuitive or crappy or whatever, right? Cosine of 0 is 1. And then as angles get bigger and bigger and bigger, cosine gets smaller and smaller and smaller, right? Sine super, cosine counterintuitive, or whatever you want to say. Why am I saying all this? Because I'm saying now, look, if you have two random vectors, if you look at my picture, say you have two random vectors, A and B, or even better, you look at the actual original physics that we're looking at here, you have two vectors, F and X, right? They form an angle between the two of them. They form an angle. If you want to see how they're related to each other, if you want to see how much F is contributing and how much X is contributing to this product, to this overall product, but you only want to look at it in a scalar way. You only want to look at how much of F, which is parallel to X, is relating to X. Like if you think about the physics here, when we're pushing a box across a floor, and we're pushing at some angle just because like we have to because of leverage or because of the human body. We're pushing at some angle, but we're trying to get it to horizontally displace along the floor. Only the horizontal component of our push really is contributing to any displacement along that horizontal floor, right? So if we're trying to relate these two numbers, the F and the X, and we're trying to say, come up with an overall product, which says the bigger each one of them is, the bigger the overall product is. And if either one of them is 0, then we overall have nothing, right? And that's the idea here. Then really, when we think about it, we want our overall product to be a scalar. We don't, the amount of work or energy that we're going to give to this block, it doesn't go north or south or east or west. It's just an amount of work that we're succeeding in, period. We only want to take into account the portion of one vector that is actually aligned with the other vector. right? We don't want to multiply 20 by 5 really, because some of that 20 is going into downward motion, right? We're pushing at an angle. Some of that 20 can be divided into two components, a horizontal component and a vertical component. 20 cosine 60 and 20 sine 60. Well, the 20 sine 60 is just pushing this thing down. That is not helping it move over. In fact, it might even be hurting it because it might be increasing friction or something. It's only the 20 cosine 60 that is aligned with the 5. Those two numbers are along this. So 20 cosine 60 is along the same axis, the same number line as 5. If we, instead of multiplying 20 by 5, if we multiply 20 cosine 60 by 5, which is the same thing as multiplying 20 by 5 cosine 60, right? Like we could tilt our head and we could say, or we could think of it as how much of the displacement is along the force axis. We could think of it that way. Sometimes that's more convenient. So then the cosine would go on the other term, but multiplication is commutative. So whether we think of it as F cosine 60 times X, or F times X cosine 60, or just simply F times X, like 20 newtons times 5 meters times the cosine of the angle between them. Ultimately, what I'm saying is what I'm saying here is AB cosine theta, which is the same thing as A cosine theta B, or AB cosine theta, means that what we're really doing, if we want the scalar product, the non-directional result or relationship between two directional quantities, what we do is multiply the two quantities to the extent that they actually are interacting with each other on the same axis. We take the piece of one that is actually lying on the same number line as the other, so that then we can just multiply two numbers as though they were just two numbers on a number line and get an answer that doesn't have arrows or north or south or east or angles or anything. So I'm saying in general now, and I know I'm watching the clock, we still have a lot more to do Wednesday. So what I'm saying right now is that the dot product, the scalar product of any two vectors is really the magnitude of one times the magnitude of the other. That's what it says right here. The magnitude of one times the magnitude of the other times the cosine of the angle between them. Because I'll say this one last other way, cosine specifically, not sine, because cosine, when you really think about it, measures parallelism, alignment. Cosine is the indicator of alignment because of the fact that cosine of 0 is 1 and cosine of 90 is 0. So cosine is just a number, a fraction that ranges from 0 to 1, like from 0% to 100%, as the angle, I'm sorry, it ranges from 100% to 0%, as an angle ranges from 0 to 90. So if two things are perfectly aligned, we're saying multiply the size of both of them and then take 100% of that answer. Boom, there's your dot product. If two things are somewhat aligned, you multiply if two vectors are somewhat aligned, you multiply by their lengths and then by this factor cosine theta, which is like some percentage. You're just going to take some fraction or some percentage of your overall answer. The more parallel the two things are, the bigger a percentage of your answer you're going to get. If they're literally parallel, it'll be cosine of 0, which is 1. It's just like normal multiplication on the number line. If they're literally perpendicular, if you're pushing up something that you're trying to move over, then it's this. I don't care how big this vector is and how big that vector is. It'd be one size multiplied by the other size times the cosine of 90 degrees, which would be 0. You would do no work. Okay, so I'm telling you two things right now. I am watching the clock. I know I'm getting myself all. I'm saying in general, this is a memorizer, and it will come up in future homeworks, whatever. In general, from now on, the dot product of any two vectors is the magnitude. In other words, the product of two vectors that itself is not a vector. This is one way of multiplying vectors, not the only way, but the one way that we need right now for this physics. The dot product of two vectors is the magnitude of one times the magnitude of the other times the cosine of the acute angle between their two tails. Okay. And then that's math. Physics-wise, I'm saying if you have a small enough displacement that it is subject to a constant known force. So I'm now saying, if you, in our example, if you had a small enough displacement that it was being multiplied by a, why is there a dot? Oh, that is being multiplied by a known constant force. You could even like put a little zero here if that makes it a little clearer. Then I'm saying it will be and this is the definition of work, and we're almost done. I am watching the time with 3 minutes. Okay. Would equal 100 newtons times 5 meters times cosine of 60 degrees. I think it was 100. It better be 100. So it would be 250 newtons times meters, which is equal to 250 joules. Okay, I'm saying 1 joule equals 1 Newton times 1 meter. Okay, so in the simple cases where displacement is small enough to be finite to render F a constant, then we do a dot product between the force vector and the displacement vector. So in this case, we would get this. But now, and I know we only have 2 minutes, now I'm going to say, however, the real thing we're interested in life here, the real thing is okay, now this is what we're going to get to tomorrow. What I'm going to say now is, if F starts varying, if it starts getting big enough from delta X to delta X to delta, if the delta X gets so big that F starts smoothly varying, like first it's 1 Newton, then it's 2 Newtons and 3, and if F is varying as a continuous function of X, then we're going to have to add up all the little F times delta X's. We're going to have to get the work that's done right here when F is one thing. We're going to have to add that to the F times delta X over here when F is another thing. We're going to have to add that to the F plus delta X over here when F is another thing. We're going to add them all together. And if we have to do it in a case where F is continuously, smoothly varying throughout the delta X, then the way to do that, and this is what I'm going to expand in more depth tomorrow, Wednesday for sure, is the continuous sum of all the infinitesimal little products of F dotted with dx is called an integral. I'm going to develop that more on Wednesday, whether you feel like you understand integrals or not. That's what we're going to do Wednesday. But I'm saying a little bit of work is F times a little small but finite amount of displacement delta X. A little delta W equals F dotted with delta X. A big amount of work when F is changing so continuously that it's changing for every infinitesimal interval of X is the sum of all of the infinitesimally small F dx's. That is called an integral. Truthfully, work is the integral of force dotted with displacement. That is what we'll do Wednesday, but that's where we are right now. That's so I'll hang out for a second for any questions or anything, but I'm good if you're good. And there's a couple of you that still have to get your game turned back. I'm going to turn it back right now in 3 minutes if you didn't. But anyway, okay, I'm good if you're good. I'm hanging out if you have any questions.
Thank you, Professor. Have a great day.
Have a good day, Professor.
Thank you, guys. Thank you. Awesome. Thank you. Awesome. Have a good day. Thank you. I appreciate it. Thank you. Awesome. Thank you. And Shamil, you're good? Or I'll turn off are you good, Shamil? You there? I'll turn off the record going once. All right. Thank you all, everybody. This has been lovely and terrific. Tune in next time when we do actual integrals. Yes, tune in next time while we do actual path integrals. Everybody's favorite home game.